So today we're going to talk about SVM. I should put the title in the whole thing. Is a still within our supervised learning framework of machine learning, where we're being given the data and the labels, and we're going to build a classification model. So this is a very different model from the things we've done already, like k-nearest neighbors was a kind of spatial amongst all the data points, or decision trees where you're dividing up all the feature space in lots of different ways. This one is about, in a way, a simpler type of thing, apologies, of way of looking at it, is that let's just divide the space. If you want to classify some data points, then you want to basically draw a line in space between the points that are, if you only had two classes, A and B, then you'd want to divide it between all those points, right? Just draw a line between them, and all the points on one side are in class A, and all the points on the other side are in class B, right? That's the simplest kind of classifier you could imagine. So SVM basically does that, but in a clever way that generalizes it beyond just two classes or to, spaces where you can't draw straight lines and all that. So it solves all those problems. You say, oh yeah, but that wouldn't work. Oh, that wouldn't work. SVM actually solves all of that, and it's the optimal way to do it if you know that your data points are fully separated. So there is a way to come up with this kind of linear separation between them. But it does require a bunch of things to be set up just right. So that's what we'll go through. And there's some, mathematical representations in it. We'll give you the high-level part of it to show you, the differences. And then we'll just kind of leave it there. So it falls into this idea of like decision boundary type of, I have this turned on, good. Approach for classifying algorithms, and I don't know if this division of algorithms is really the best, but it's just kind of one way of looking at it. We've had naive Bayesian logistic regression, where you're using kind of a probability as the thing that decides which points are in one class or another. And then we had this kind of more spatial thing where we talked about the nearest neighbor, which is related to that. We're not talking about all these methods. So there's different ways of dividing up the algorithms. So SVM is kind of a little bit older, right? So this is the thing that's all exciting now. And, decision trees are 80s and 90s. Random forests are 90s and still great. SVM was all hot in the 90s, and now it's like maybe, and even the 2000s, it was the main thing everyone was excited about. And now deep learning has kind of taken over, because in a way, well, the most complex form of support vector machines use kind of kernels that map input points to output points in a dynamic way, and in a way you could actually reproduce that with deep learning without having to do all this tuning. So using this model is very useful, because it's kind of fast and very direct if you know what the properties of your data are, and you can apply it. But it's maybe not as general as deep learning, because it can learn these things directly. So if you have a lot of data and time to learn it, deep learning should always beat this, but you don't always have all that time. And for smaller data, this kind of targeted approach of SVM is going to work better. So can everyone see my slides? Some discussion in the chat here that some people can't see it. In my little preview of it, I can see it. Okay. Okay, hopefully you can. The slides, I did upload the PDF of these slides onto Learn. We're on slide 4 right now. And as always, it's going to be recorded and posted up onto YouTube after. Okay, so SVM, like I said, it's a way to separate classes using a hyperplane. So you could just call it a line, but we're going to be fancy and call it a hyperplane. In the simplest version, this is just going to be a line. But in more than 2D, we're going to say it's a hyperplane, right? And it really is just a flat surface in however many dimensions you have for your space, so it doesn't mean anything really more complicated. And as always, we want to build a classifier that works on the test data, right, that we have, but also, it's trained on the training data, but it works well on the unseen examples, right, which is what we've been calling the test data, right? So it generalizes well the data it's never seen, but comes up with a simple model based on the training data it's been given. So here's the main kind of idea. We have a bunch of data points. In here we're going to be doing the 2D version for most of our examples, because that's how we're limited. Right, and so we've got the square class and the circle class, and here it's perfectly easy because they're very well separated. And I want to say, give me a classifier that always tells me, you know, basically set it to say that this classifier tells you if it gives you a positive result if the data point you give it is a square. So they give you a new data point here. Wow. This worked before. Yes. Okay. If I give you a new data point here, then I want the model to say that it's in class 1, right? I guess one of the trade-offs then, when you're doing this, you know that they're fully separated, so you can draw a line to divide these. But which line should you pick? So this is the question that SVM answers, right? So you've got 3 different lines here. Each of them works perfectly well with the training data we've been given, but which of these 3 lines would be the best to use? Yeah, right, someone's asking about D, where D would be the number of dimensions. In this case, we're saying D equals 2 here in our picture, but if you have 10 dimensions, then each of your points will have 10-dimensional point. So which of these lines would be the best? We got lines 1, 2, and 3, just intuitively. Two, right? Yeah, right. Why? Right. 2 is the line that goes straight between them. It's kind of doing this regression fit or whatever. But what's the real intuitive reason? 2 is the best line according to SVM because if I get new data points and data is distributed the way we think it is, then this line number 2 is probably going to capture the best performance for new data points we haven't seen yet, right? If we're right that all the data points in class 2 are kind of over here and all the data points in class 1 are over here, then new data points, line 2 will get less of those wrong, right? Whereas this red line here, line number 1, it's immediately going to get, any squares wrong that happen to be over here. I mean, we could be wrong about the distribution of these classes, so maybe it's over here, but the general assumption for SVM is that you want to have a line that maximizes the space between these classes as much as possible, right? And so we explicitly call them optimized for that by this thing called the margin, right? So our line is defined by, usual, just like a linear equation here that tells you what that line is. And then we define something we call the margin, which is we say, what's the distance perpendicular to that line to any of the data points from the 2 classes? And you pick the smallest distances from that line to a couple of the points. And what's the first point? What's the closest point you can find in the data set? And that's your margin, right? So if these 2 points are the closest ones, then the margin is going to be, you know, something that just barely doesn't include these points in the margin. That's our margin of basically, not error, margin of like a buffer, right, for us. Whereas if we picked a different line and the margin was much smaller, right, because here now we put one at more of an angle, there's very much less gap here that's basically given over for us to find new points that are not already in the space of ones we've seen, right? So if you're given these two lines to choose from, SVM says choose the one on the left here because it has a larger margin, right? There's more space, more gap for it to be allow new points when they come in, right? Yeah, and so people are right, you're talking about a buffer, you're talking about the distance to the current data. And so we want to make this explicit. And so in support vector machines, what they do then is define this explicitly. I had some extra math here. Right. So the core thing is the formula for our line here, right? This is the line that we're trying to define for our separator, right? We have a bunch of weights, which are computed on every one of the data points. So every data point has some weight, and we can define the line on that. And we have some buffer, like bias term that we can use to shift the line in space, right? So we were trying to come up with this formula and come up with the W's and B's to define this line, right? But we want to do it in a way that maximizes this margin, right? So if we say now, let's imagine that you're at this point for the line, right? And then that's where it equals 0. And if you had +1, we say that that's what this line is. And if you had -1, you define this line, right? So we could say we have these two formulas which define the next two lines. And if we then say that what we really want is we want all the positive points plus b -1, and then we have just combine them both together. Data points. Oops, sorry. My little focus thing here helps me write more neatly, so you're getting that preview. We just combine them together, hoping that this is going to give us m. I forget how I wrote it out first, but and when we simplify them out, we end up getting that, right? So we'll have all our data points that are positive and negative together, and we'll have this -2, I guess, equals 0. And then that gets us to our formula up here, where we say this is a definition of the line we want, where we say we have the weights set up in this way, and we have data points that are positive and negative, which we know because they're given us in the labeled data. And we want to say that there's a size of 2 on this margin, right? So when we reconvert it around, then we say that basically we want to maximize twice the margin. That is the same as minimizing the magnitude of all the weights we have and half of that, right? And the magnitude here is just the L2 like Pythagorean distance of all of them, right? So we're squaring all the weights and square rooting them. So what we're trying to do, though, is create up an optimization problem, right? So we want to minimize the weights so that we're maximizing the margin that we get here. And m is a thing that isn't known, but it's dependent on the weights we're getting, so that we make this line as thick as possible. So we're trying to set up an optimization problem, right? T is transpose, yes. Sorry, capital T is transpose. The lowercase plus here, I guess it's harder to write in my messy writing, is just the positive data points and the negative data points, right? And we're saying, I mean, if positive in my set, I said here, so if the point is in class 2, that's going to be positive. And then I guess the negative data points would be class 1, right? If we're talking about binary, we pick one of the point classes arbitrarily to be positive or negative. Okay. Yeah, so then I had a demo thing here. Let's see if this works. Forgot about this part. You guys can see that. So I will set it to linear. So the idea, right, we've got a bunch of data points, and let me remember how this demo works, right? We've got our green points and our red points, and as they get added, it has to, adding because it gives me red, right? Okay. Reset. As you add more points, it has to adjust its lines, right? So since these, if you think about what we've done here, is essentially coming with this distance to the nearest points to the line, right? And so these are the things that we call the support vectors, because, why does it do that? Only with my mouse. The support vectors are the data points that define this distance, right? So if you have a number of points that are tied, they'd be support vectors. Basically, any of the weights that are not 0 in our optimization become the support vectors, because a lot of these ones, they're going to be not relevant to this optimization, so they'll all be 0 and basically irrelevant to the line. But a few of the ones near it will be non-zero. And that means they could shift the line, right? So I add some new points out here. It's not, well, that one has, I guess, more of an impact because it's further from the prediction. But if you add points that are near things you've already seen, it shouldn't change things much, right? If you add them near the line, it won't change things. But if I suddenly try to add one, on the other side of what the line was, it now has to shift the whole thing over to fix it. And you might notice that the margin is, well, getting smaller. It isn't because they're doing the other thing, which we'll talk about next, which is what if you can't get an exact answer? And I can add green points too. So, but this is the main idea, that we're just trying to fit this line at this initial stage so that we balance it. And if some point is inside that line, it becomes now part of the support vector that computes that. Could it be worked on streaming data? Alex is asking. Yes, I don't see any reason it can't. I'm trying to think if there's a limitation. Well, it depends on how you're solving this, right? So if you're iteratively working out to decide how to, like when we add a point like this, how do you solve with all the other points? So usually, traditionally, it's not a streaming method because the way this is solved, which is a nice lead into the next part, is we turn it into an optimization problem. So you need all of the data points that you've been given, and you compute the support vectors and the weights, and then you get an answer, right? And so now you've got, we basically turned the rule we worked out there into an optimization kind of definition. So we're going to minimize the weights subject to this condition that it has to be a valid line, where we want it to be 1, right? So plus 1 were the positive points, so we're basically getting a line for the positive case. And then once we've trained this optimization problem, all we got are these weights. So now we've just got a line, and we put our new data points that we've never seen before into that formula. And if it's positive, it's class, what did we say? Class 2, the positive case. And if it's negative, it's class 1, right? And so adding new points after the fact would actually be hard, because then you can't just incrementally change the solution to this optimization, right? So you'd need to have a way of optimizing it where you could add new points and smoothly update these. So it's a bit tricky. But when we're interactively dealing with this one, it looks like it's streaming because he probably just like deletes all the points and recomputes it every time you click. It's pretty efficient. Yeah, so actually for multiple classes, today's things, as I was thinking through the notes, explaining through the theory of it, we always just talk about 2 classes. because that's what it's best used for. So if you had many different classes, we can talk about that after, but obviously, yeah, you could do a series of binary things, like picking it for each class and figuring out if it's in the first one, if it's in the second one, and kind of recursively dividing it. But we'll have to go to talk about that more once we finish through all of the basics of it. Okay, so it's an optimization problem. So what did I have next? So that can be solved in various different ways, right? So you could use quadratic programming, you could use interior point methods, you could use KKT. So there's this, do I have this? Using Lagrange multipliers. Oh, I have 2 slides on that. Is that right? Yeah, okay. Right, so I guess when you're doing it with that basic optimization approach I put here, it does have this problem because you have to have, once it gets set up, you have a weighting on your formula here, an alpha, which these are the support vectors. And so there's a bug in the way that it can be done because you could just set them all to infinity and you'd find an optimal solution. So that's not good. So they have various improvements on how to actually formulate it so that it optimizes better. And so if you do minimizing these weights we have and then trying to maximize this alpha weighting, then you get a better formulation for it. And so this leads through to more to like the way that people actually use it. So that's why we're leading through a couple different formulations that you probably don't want to use if you're defining it. So once you create this alpha here, rather than just letting it be the weights for every, I guess that's the way of saying it. I'm not sure if that alpha needs to be there. If you just have the weights themselves, you could have all of them contributing in different amounts, right? But a more efficient way to do it is, like we said, to have this alpha weight that says, let's also optimize another weight which says which points are the ones we're going to actually use, and all the other ones will be 0 and we'll just ignore them, right? And so you create this alpha I, which says that only the ones that are needed to optimize it will have a value and everything else will be 0. And then that basically puts in so that the weight we're learning is not just the combination of the data points, it's including this alpha. So that becomes part of the new objective function. But then even that kind of isn't the most efficient way to do it. So in optimization, and it'll go, it's not an optimization course, so it's not area I want to go into too much, but there's an approach called dual methods, right? So you take you basically invert the problem. So when you're going from minimizing one aspect of the problem, you go to maximizing a different formulation of it, and so it's called taking the dual of a problem. And in this case, what we end up getting is to have something where we're maximizing these alphas. So we're trying to find the data points, the support vectors that specify which data points we're actually going to use. We want to maximize them as much as possible. So basically come up with a few data points that are going to become weighted highly to build this line to depend on. And then we have this other, when we go through to converting it to dual, all the math gets flipped around. And so we've got now the data points xi, xj, the labels yi, yj, and the support vector weights for the same data points, I and j, right? And remember, these alphas are going to be 0 for most of them. For the ones that are not 0, this will be meaningful. And we're trying to maximize this whole thing. And I guess I'm missing a bracket there. And we're trying to maximize that to the fact we're saying that the labels basically cancel out, right? So you should have enough, the same number of support factors on both sides, and the weight should be equal. So if you decide that you need 3 points for one class, you need 3 points in the other class, and they should balance out given the scale of those labels, but that the weights are still never negative. And so when we maximize this, that becomes the most efficient way to solve it. And we can use, like I said, these quadratic programming or other gradient descent methods to analyze that directly and come up with a solution. Right, and so the vector we get is the vector of the data point, the data points that are still included, where the alphas are not 0, and we get that solution. So this still has a couple problems. This gives us a more efficient way to solve it, and it can deal with large dimensions, but we're still talking about a linear hyperplane, right? So if we've got a bunch of data points and I try to draw it in 3 dimensions, which is of course very hard, you know, what we're defining is, you know, not just a line through space, but a hyperplane through all these points, but it's still straight and flat in those dimensions, right? So clearly it only works if data points can be separated by a straight line. And so there's 2 ways to solve that. The first way is by what we saw already in the demo script there, is that you allow for some error, right? So these are going to be called slack variables. And then the other way is to say, let it be not linear, but still use this algorithm. And for that one, for that part, this formulation is going to be important. So the fact that we've got it formulated this way becomes important for the way that we're going to solve it to give us a nonlinear method, because essentially all we have here is dot products of the x's and the y's, and that means we can replace it with something that lets us go from linear to nonlinear, and this is called a kernel method, which is really the broader class of what support vector machines are about. All right, so which slide am I on? Okay, so yeah, we want to allow for some error on the training data, or error in our line, that if it's not fully linear, we can solve it. And that's the first kind of change that we add to it, which is called this soft margin SVM. So in soft margin, we're going to add one more variable, psi, I forget how to say this one, squiggly Greek symbol, psi. And what we're really going to allow then is to say that sometimes your point could be out, and we're just going to kind of penalize you, right? So in this case, we've defined the line, right? And we've got some support vectors that are defining this line that are set to alpha not 0. And but now this point comes in and he ruins the whole show, and he's on the wrong side of the line and everything, and say, okay, basically, so should I move the line? Should I just delete the whole thing, or should I just allow it, right? And so we come up with a slack variable that says you can accept a certain amount of error, but then that becomes part of your optimization as well. So you try to minimize these errors, but you can allow a certain amount of it. And then there's a weight that controls how bad these errors are. And so that's what gets us in this class, where we can say now, you know, I added a red point on the wrong side of the line, and it's still possible. Didn't have to move that much because it's there, but it's feasible. There's a way to do it. I guess at some point, if I add enough things, it breaks the whole thing because it's not feasible, right? But you can still get over it a little bit because you're just being penalized for these. And that's what this C variable basically controls, right? How much penalty there is for getting it wrong. So now we're going to be basically minimizing what we had before, but we're going to add these slack variables, and we're going to have a new weight that says for C, which is this soft margin. So we have a margin, but it's soft, so it's got holes in it, and we allow some overlap into it. Right, and so we're summing together these costs, and so psi I is adding the margin that gets added by that new point, so how far you are off. And then we just add them all together to that target function. So if we have a higher C, right, that means it costs more to use these slack variables, right? So we're basically multiplying them by something large. If C is small, then we don't care much about these errors and we allow a whole bunch of them, right? So if we basically set C higher, then the cost is higher and we're less lenient towards errors, right? And so if we go here and see what I've done, so I added in a point that broke the initial line. If we had C to be higher, it really doesn't want that, so it tries to find a way that fixes it. If we set C to lower, it's like fine. Oh, now I'm setting it higher, sorry. This is the way it's going higher. And now it allowed it, but it had to basically fix it. So if I go lower, it even allows some of the points it already had to be on the wrong side because it's trying to be the most general. It's trying to get away from these negative points, so it accepts some of the green ones being on the wrong side. So that's this new parameter we have to adjust. Okay, so that solves the error part and things not being linear. Sure, we can explain it again, slack variable, right? So we've got the slack variables here, right? We've got our data points, we've got our support vectors. When a new data point gets added, I mean, it's not like, I can say that because that's how we think of it intuitively, but we're not adding new data points. All the data points exist at the beginning, right? So the interactive one is making us think that. But if you have data points in your set, so if we didn't have these 2 points here, the new x, the new circle and square that are outside the normal ones, sorry, these data points, if they weren't present, we would have come up with this line, right, with no slack variables. But now, if they're considered inside the data set, then it's like it's really throwing off the model. So we have one perfectly good line we could fit here, but this point is kind of an outlier. It's off in another direction. And so for every point we have, if it's inside the margin, we get this new count, right? So for xi, we got a psi I, which is how far it is from its own inside margin, right? So we give the distance from this class is kind of inside to its point, and we use this distance as essentially an error, right? And we have another one here, right? And so what we're trying to do is minimize these while we maximize all the other things we had. So all the points are existing in the beginning. I mean, these all have a psi I as well, but they're 0, right? Because they're on this side of the line. So that's all we're doing. We're adding basically another cost. It's not about streaming because the data is all existing in the first point. It's about basically having every point have an additional cost associated with it, which is it over the line or not? We'll allow it to be over the line a little bit, but they all have to work together and not be too far over the line, right? So yeah, that's a confusing way of the fact that I'm showing this demo makes it feel like it's a streaming thing, but this is all here in the beginning, right? We have the data, and you can compute this cost based on any line while you're optimizing. Every line you pick will have an implication for the psi soft margin error for every data point, and you want to make it so that most of them are 0, and even the sum of the ones that you have are small, right? So we add this on all data points, right? It's just like we have a weight on every data point, we have a psi on every data point, and now we're trying to minimize not just the margin of the line, but the margin minus all the costs, right? And right, and so we actually have a constraint that it must be positive for all the data points. right? And then once we're optimizing this, it's going to find a solution that is consistent for all three of these now, that finds us a line that minimizes the error. But that means for every solution, if you change the C, you would have got a different line, right? So hopefully that helps. Okay, and so then the other part that we were missing was with the two limitations, right, that I mentioned before, which was errors, slack variables, and the other one was not a linear solution, and the solution to this is going to be kernels. So this is a very important method that applies to many different domains and helps actually understand a fair bit of neural networks. So sometimes when people talk about SVMs, this is the main thing they would talk about. And I don't think it was necessarily invented for this, but it was put to very good use for this. And the whole idea of a kernel trick comes from this, this literature. So what's the problem? Right, the problem is we're still talking about lines, right? Even though it's lines in high dimensional spaces, it's still a flat plane in that space, right? There's no curves or anything. But what if you had a nonlinear kind of separation between the data points, right? There's just no really good way. Oh. What if there was no good way to separate them because all the data points were on the outside from one class and on the inside for another, right? Can you do that? Not with a straight line, right? And it could be any kind of irregular combination. Most data sets have some kind of irregularity in it, right? It also requires all the features to be the same kind of length and dimensionality. All the dimensions have to be the same size if we have a line like we're doing before, right? And in our text document things and in other data sets, some of the features have a small range and some of them have a lot higher range, right? And so that seems like you can make it more complicated, right? So what we do is we define something called a kernel function that lets us not worry about finding a new set of features, like because we talked about feature extraction and PCA and all these things. You could come up with a better set of features that do that, and that works well for SVM as well. So you can take your data, do PCA to it, and then do SVM on the PCA features, and you'll probably do even better because it's oriented differently. But kernels basically let you have your cake and eat it too, come up with something that lets you run this algorithm, but doesn't compute the features directly. Because, well, I mean, a kernel is basically a distance function between 2 points, and so you come up with a different distance function that holds in a different space. Sorry, my next slide on my paper thing is different than the one on this. Sorry, I don't know where I am now. What is going on? Okay, that's the slide I was looking for. Yeah, I'm gonna have to fix myself because I noticed when I was just before I was looking to prep that I had some duplicate slides and stuff. So I will fix the slides after. All of the data is in there. It's just the order was a little weird. This is the one I wanted to show next. Basically, what a kernel does is that we want to come up with this mapping, right? We want to come up with a new nonlinear mapping from the points we have. So say we have our 2D data set here, like I was showing. You have something that's maybe a bit more circular and hard to fit a good separator to this. And this is in 2D. and then we're going to pump it through some function and give it a new space, so that in this new space it's 3D, but that we can fit a nice straight plane that separates them, right? So you can imagine that you say, okay, well, these data points have a lower height, a lower z, and these have a higher z. So we could come up with like rotate these and add a new dimension so that they're now nicely linearly separated, right? And you can probably almost always do that, right? That for some kind of shape you have, if I let you add enough dimensions, you can make it so that the data points that were contained in some kind of circle or weird curved structure in the original data space are now separable by a nice, neat plane, right? The question is, how do you come up with this function, right? So that is a hard question, and there's no answer for it because good practices people use, but coming up with this function is, computationally intractable for any large problem to come up with the perfect kernel, right? But there's a lot of ones that work very well in practice, and that's why SVMs were popular. So this is the basic idea. We're coming up with some way to turn these data points into a new space with a few more dimensions that makes the algorithm work. Right, and so trying to figure out what this mapping is challenging, but there's an encouraging trick in the data. So when we looked at the dual problem, right, remember I said that essentially at the core of it, we had this calculation of the data points transpose the data points, right, which is just the dot product of the data points themselves. And so it doesn't really need to know, in a way, the features of x and of xi and xj. So in a weird way, we've been talking a lot up until now about what's the right features to represent this data point, and once we have really good features, we can do something interesting. But kernel function says, I don't care about the features. All I care about is, are these 2 points close to each other or not? Right? Because what we're trying to do is maximize, this line that keeps points far away from each other. And so if you can give me a function that tells me if any 2 points are close or far, I don't even care what their features are. I don't care if they're made of, atoms or features or numbers or words. Just give me the distances, right? So kernel function is just that. Just give me the distances. And that means you can come up with a different set of distances in, say, a higher dimensional space, but you never have to work out what their actual x, y, z position of every point is. You just have to be able to say, are these points close or far? That's the main intuition about why kernel functions actually save a lot of computation. That doesn't necessarily help you understand better, but that's one way of thinking about it, because they're a bit trippy, right? They basically are some function that takes an input of the x's and y's and gives you a new number as an output that satisfies some higher dimensional space requirements, right? But the result is that we can use it then for the algorithms in a very clean way. So I'll just show a bit more detail on that and give you some examples, and then we'll get to people questions. There's a lot of different functions people can use for this. So here's the relation we're trying to represent. So we're given some data points. It has some particular phi function that we may or may not know, and the output is this kernel, which gives us basically a matrix of distances between points, right? All the points. The only requirement is that they have to be real numbers. They have to be positive. It's usually symmetric. So if I do it in one direction, the reverse of it should be the same. And usually it has to be positive definite, right? So the all the values of it should be positive when you kind of combine them together. And there's some kind of more finicky kind of requirements that tell you that, specifically, some formulation of it, the gray matrix has to be positive definite. So if you build a matrix, this is the graph matrix of like all the data points, in a matrix, then this should be positive definite. So all the elements should be positive. But basically, as long as you satisfy these, and a lot of different functions do, and people have lists of all of them, then you can use them as a kernel. And like we said, you don't even have to actually come up then with these phi's. You just say, I'm going to pump data points. If you give me 2 data points, I'll use this formula to give you a distance, and then that's what we'll use instead of the dot product. So basically in the SVM code, any place we have in the dual form, any place we have x transpose t or dot product, we now use the kernel instead, and that means transpose as well. So there's different forms of transpose. Well, it's just a different version of the same matrix. So you can have a Gaussian function that basically says that there's a problem, like the distance you give is sampled from them being in a Gaussian of each other, so how close they would be that way. Radial basis function is a popular one, and I'll show you the example of that with our tool we were showing for the demo, because it basically says that there's going to be like a circle, a soft circle around every data point, and if you're closer to it in that sense, then the distance is higher. And then there's some bug here that I have to figure out, because in my old slides I had xij, and I don't know when I switched it. But for documents, like for words that we're talking about, you could use cosine similarity as your kernel, and then basically do SVM on the words in that way. I have to figure out where the j is supposed to be in this. I'm not sure if it's supposed to be that. I have to go find the notes that these came from originally. Oh, right, and I did figure out what this error was. This should be phi. But you also just use the TF-IDF score we have directly as the phi, because it's not a distance, but it's kind of a magnitude. And if you use that to basically build a kernel by having them combined, then you'd have something that uses that TF-IDF score directly and tells you if 2 words are similar to each other, because their TF-IDF scores would be kind of different, 2 documents, sorry, on different words. So if we use this in our demo thing, he's got it, I can toggle to the nonlinear version, and they are using the RBF kernel, right? So this formulation, so distance on a circle between the 2 points, kind of a Gaussian circle. And so we still have the points we have here, we still have the soft margin that we talked about. So if we decrease it and allow more error, we can get it to give us some really weird other shapes. And if we add more data points, sorry, I'm adding red. Oh, I guess if we add enough red, then it decides the entire thing's red. That's surprising. Okay, so if I stay inside the original one I had, it doesn't change the shape too much. But if I start adding ones out point, at some point it decides like, well, maybe everything in the other area is red. If I add more greens, then it'll do the same thing. But now it can handle a nonlinear thing. It can even go in beside each other, because you can have a circular function around every data point and say, okay, these are all connected. But what it's really doing is it's saying, using this RBF function, so the distance between 2 points is not the cross product of their features, but the output of this function. I use that to determine their distances and use that to optimize the line, and now I'm fitting a flat plane, but in that higher dimension, which is defined by the size of this matrix. And so, okay, sigma. So in the basis function, we have this sigma parameter at the bottom, which I guess controls the roundness, I think. Yes, right. So the higher that is, the more it wants that function to be something that's really round over like a large size, the size of the circle that it thinks is using. If you make it smaller, then it allows little small circles around every data point. So it seems quite flexible, right? You can handle pretty nonlinear data. on this kind of thing. And so in the 90s, when this got kind of put forward, part of the reason, when we get to neural networks, we're going to talk a bit about the history of it and why like neural networks were reinvented a couple times and never, people got excited and then gave up on it because it wasn't that exciting. So the second time people walked away from neural networks was kind of a bit because of this, because people saw this like, this is pretty exciting, this works. I could fit any data with this. All I have to do is put an RBF or some other function. It's perfect. Why would we ever need anything else? And eventually, Jeff Hinton and Yann LeCun and Yasha Ben-Gio came up with the reason why I should think of something else. But so they're still very useful because they still work, and they're faster in a lot of ways than deep learning and don't require as much data, but they do require you to come up with a bunch of these parameters and these functions. So if you know something about your data structure, you can set them up this way and use it. So once we have the kernel specified properly, using the dual form, which we had before, like I said, instead of having, doesn't it show it? I was sure I had it. Yeah, maybe I should have this slide earlier. This is still just using the dual, but like I said, you've got the objective you're trying to optimize, and these subject to constraints you're optimizing, and you're trying to calculate the weight so that only some of the data points are support vectors. But now instead of, okay, it does have the kernel in there, right? So instead of before where we had xt of xi, well, I guess you don't even have to have that. If it's two sums like this, that's the transpose by default. So before it was just xi, xj. When we're saying xt, the form where it's using the dot product, right? That would mean that there's that there aren't any sums because all of the variables here are just vectors, right? Maybe I should make sure we have the vector form and the sum form in there. But these are the two different alternate ways, right? So here's the original way, and there's the kernel way to represent the same thing. And then, like we said, I don't know if we said that clearly. I said it on the simple version, but once we have all that, we still just have a line, right? And we have the W's and B's. So we're giving in a data point that we're trying to classify that we haven't seen before. We basically put it in and say if it's greater than, if it's positive, then it's in one of the classes, right? Because that dividing plane now is still creating that difference. But it's an interesting question. So Ling Feng's asking about, is RBF and k-means related? We actually haven't talked about k-means, so that's looking ahead, which is fine. So let's go to the, is there space on the k-means slide so I can save this after? We'll talk about k-means, clustering, maybe tomorrow, I think, if it's in my clustering slides. So here's a little preview. It's different. I'm trying to think as I draw this how it's different. So you have a bunch of data points. K-means, well, k-means is for clustering as well, right? So we have some data points in that problem. You don't know what the classes are, right? And so you're trying to come up with a shape that represents a space between them by specifying kind of a center point and then moving it. So it's actually quite different, right? You are defining circles and moving them around to decide if these points are together or not. But it's it's only a circle because you're talking about distance from the points from the center, and you're moving that starting point explicitly. Whereas, in a sense, you're right. There's an intuition. There's a bit of a similarity because in the radial basis function, if it gets turned on that these points are kind of close together, then you're drawing a circle around the ones that are close together. but it's done a lot more dynamically, right? So all these points are in the same group because of the distances on that. I mean, you're right, there's some similarity. I hadn't thought about that before, but it's somehow, it's built in a very different way, right? Because we're defining this function as an optimization and what's the optimal way of doing this, whereas in k-means we are searching essentially for circular or ovoid regions around data points and moving it iteratively. So it's built in an entirely different way. But I wonder if there's a correspondence between k-means and RBF that could be found. So Sanger's got the big question, how do you choose the kernel function? And I don't know. There's no basis. So if you search SVMs and read about it, there'll be whole lists of different kernel functions you can use. RBF gets used a lot, so you try that first. And there's Gaussian kernel, there's polynomial kernels. You can basically come up with any combination of, add, feature 1 and feature 3 and feature 1 squared plus times feature 5 cubed, every combination of those, and add them, each of those is a new feature. So you can keep hacking kernels any way you want. And so in the 90s, like when I was in grad school, hacking kernels for SVM was like a thing people did, and I'm like, this is strange. But you can come up with a kernel and maybe it'll work really well for your data set. It's better to use ones that are kind of standard, so you're not just trying to game the system you're using. But it's one of the parts of this that it's a really clever idea. It just needs that answer of what is the kernel, and there's no simple way to come up with that. There is one other thing, and I guess I won't drop this. You can even build linear kernels, right? So you can just build any function you want that just puts the points into a different space and just combine them with the actual dot product and then use that as your kernel, right? You're still assuming then that the features are linearly separable and independent, but it can be a useful way to kind of basically add a bit more distance or dimensions to this. But it doesn't answer your question. So there's no known way to come up with the optimal one. There's rules of thumb for different data sets, I guess. But one way of thinking about what neural networks are doing is that they're they're drawing lines like this between data points in the system, but in a kind of very nonlinear way. And so you can basically specify a neural network such that it has almost the same structure as this, and it learns the kernel, right? So if every possible kernel was available to you and you could spend all your time optimizing it, you could try to learn it from experience, and essentially you can make simple forms of neural networks that try to learn this directly. So if you're trying all the standard kernels and they don't really work and you've got a lot of data, then you probably want to move on from SVM and say, let's try to learn this more directly. But if it works, it's an easy thing to try, and it'd probably be much quicker to implement and deploy than a full deep learning system. It's just a bit more limited because, there's an infinite space of these things, and it'd be pointless to spend all your time trying to figure out the perfect one. Yeah, I don't have a list of like this data set used that kernel and that data set used that kernel, like I said, because it's not the area I'm using things for. But I'm sure we can find a page that kind of lists a bunch of things like that. RBF is used a lot, like when people do comparisons in academic papers these days to compare it to SVM for some kind of other classification model they're using. You almost always see people doing SVM with RBF. That's like people's go-to, because this can handle a lot, right? It handles kind of arbitrary shapes, circles, they can be disconnected. You'd have to get pretty complicated things to say that RBF would not be able to come up with something useful. You have to adjust for these parameters, like how much slack and how much circular. So optimizing these parameters is a big part, but that's another part of it. Okay, let's see if I missed any slides because I jumped around a bit. Yeah, I think I had just duplicate slides. That's what was confusing there. Okay, so but that's the main points on this. What did I had? I realized I don't have a summary conclusion slide, and I saw a nice pros and cons of SVM. Yeah, so it's useful for things where you have high dimensions. Apparently people find it useful when the number of features is very large compared to the number of training data. So if you have high dimensional data, I guess high dimensional data relative to the size of your data points. So like we said, you don't have huge number of data points, but you have maybe a lot of features and it's a complex space. Then when you kind of turn into these kernels, you're altering that space. And if you know the data as like really good clean separations in some way, or it should have a separation, that there's a big distinction between the two classes, even if it's nonlinear, then it should be effective. But it is very suited to binary classification. If the classes fundamentally overlap, that's going to be a problem. Like the slack variable helps with that, but it's not really going to overcome fully overlapping data. Like if the data points are perfectly intermixed all the time and it's just a mixture, then basically you don't have a very good feature space to tell you how they're separated, and it might just be fundamentally hard to learn. Let's see if I can find a quick answer to the other idea of a multi-class. Yeah, one versus the rest, which is good. That's what we talk about tomorrow anyways with anomaly detection, if we can get to it. So if we had, my initial idea was that too, and I wasn't sure. One versus all, like I said, when we talk about tomorrow for anomaly detection, we'll talk about this as well. Essentially, you build an SVM that's good for classifying. If we have, 5 classes of data, we could make our first SVM, to be it's good at distinguishing A versus anything in the others, right? Right, and so you build a single one that does that, and then once you have that split, then you could build another SVM that separates the next class, right? So it's not very efficient for that kind of thing, but if it's good for separating a couple classes that have a big distinction, that's a major way to do it. In anomaly detection, which is an unsupervised problem, we're basically trying to find data points that are very strange, right? And so this actually is a little bit more of an efficient approach, because you could say, well, I have an SVM that's really good at capturing all this data, and so I'll train one that is like good at capturing normal data versus abnormal data, and you can have it being one versus all, and it makes a lot more sense that way. So it's a popular approach for that idea of anomaly detection, which we'll be talking about tomorrow as an unsupervised learning problem separate from classification. But for classification, it's focused on binary. There might be more clever ways to do it that I'm not familiar with. But.
Hey, I don't know if we have more content that you want to review.
No, yeah, so we're done with the thing on this. So if you have questions, go ahead.
Yeah, if we could spend some more time looking at the derivation side, so going back to the original optimization problem. I got pretty lost on those technical details. Just like the full formulations for margins and how somehow minimizing the magnitude of the weight vector gives you a high margin kind of.
Okay, yeah, because I don't necessarily go into the derivation for the dual and all that kind of stuff. It's not an optimization course, but this fundamental idea. Sorry, let's see where I had it. This one. Okay, yeah. So the weights define the angle of this line, right? And so what we're saying is, maybe go full screen, make sure everybody can see it fully. We're going to arbitrarily, rather than just having a line, we're going to say that there's two sets of data points. There's data points that are on the positive side, so they're in the class we want to identify, and there's points on the side that are the class we don't want to identify. So we're just labeling those as the x plus points or the x minus points. And we want to give them a bit of a score, right? So points that are in the class we want, we're going to say that the line is here. So +1 is essentially the formula for this line. And for the negative points, it's going to be this line. So we're really trying to optimize two lines at the same time. And we could say that's their formulas, right? And so if we just say that we're going to basically say the margin then, right? Because what we're trying to maximize is we want to maximize this margin, right? Which is m. And so this number m would be the subtraction of the two lines. If the formula for the first line is wx plus b equals 1, and the formula for this line is wx plus b minus 1, if we subtract the two lines, we'll get m, right? And so that's what I was doing here. I don't know if I did it correctly. I think so. So once you subtract those two lines, you get a simplified version. And essentially then we could say that the thing it's going to equal is 2, where 1 is just the arbitrary width of the margin. 2 is the combined version of it, right? Because we're subtracting them. So we're going to get 2. Which we knew because we're saying we're subtracting something that is equal to 1 plus minus 1. But the result of that, though, is the way they relate, because what we really want is a way to represent w in terms of all this, right? And so then we just move it over. What is m? We're just going to call... we're just going to call that m, right? So m is just, it's defined to be this, right? Because we don't necessarily, the distance here doesn't have to really be 1. It has to be whatever it is, right? So when we're defining it for the derivation, we just use 1. But in the end, then we replace it with m, I guess. Because the value will change based on the actual data, right? And yeah, so that's why... so now we've got 2 over w equals 2m, and we're saying we're maximizing m, then we want to minimize these, right? Because as the weights go up, this number is going to get bigger, right? As the weights get bigger, this number is going to get smaller, so the margin will go down. So we want the margin to be higher, right? We want this to go down, so we want the weights to be reduced, right? Because that would be 2 divided by a very small number, and the margin will be higher. The weights, right? Because what we're minimizing is the distance, the scale of all the weights, right? So it's our w of it, sorry for my messiness, is just going to be the data points squared. Sorry, that is not going to be readable. It's going to be the sum of all these data points, but is it x of all the weights? Sorry. Yeah, I'll have to check exactly. Right, it's the usual thing. so we want the weights to be as small as possible, but making this margin the largest. And then all the later things are basically reformulations of that to make it more efficient to compute the optimal bit. Hopefully that helps a bit. I'll try to find some other content that might help if people are still having trouble with intuition. But the idea of that line, does that make sense? What we're trying to maximize?
Maybe, okay. Like, I just don't understand. Sorry.
That's okay.
Go ahead. Yeah, no, I'm still kind of lost. I don't know if it's the notation of what x plus and x minus are. I mean, I don't really understand the formulation of the margin lines and like how that corresponds to the support vector data points. Like in those line equations, W transpose and say positive sample, like how is that a definition of a line?
Right, because it's the way for each. I guess I'll try to write it out in a different way with a bit more time then, right? Because every data point and these are just sets, right? So the x plus is all the points that are in this set, and WT is like there'd be a weight I for every data point xi, and you're just multiplying by each one and adding those, right? So it's the sum over I, wi xi. But I can reformulate it. Maybe that would it might make it clearer. You're right. And the relation between m, right? So the other essential point, I guess, is that where do we get the m from? When we're trying to maximize m is implicitly done here, right? Because it's the distance from that line to the nearest of the data points. So we're not showing the calculation of m itself, which is a bit confusing. So I can add that too. Okay. So I'll get back to you on that. We'll get something better for everyone to look at because we're wrapping up in time here. Someone's asking about 3 classes, so we're talking about that. There's different ways to do multiple classes. There seems to be various variations on pairwise versions of SVM, either one versus all the points, or every pair of one versus all the classes, or every pair of classes, and try to build a separating line between them. Yes, so Sangar's right about, he's saying that, for all the data points that are in the positive class we're trying to find, the line would give you a positive. That's the idea. I don't think m is the slope, as someone else is suggesting, because it's the distance to essentially the nearest points from that line. Right. Okay, but I will, yeah, the way I have it represented here is kind of I guess, of an older slide that I've kind of kept reworking, so maybe it's time to come up with a different formulation that makes it these more explicit, so I would do that, thank you, and we'll post it up somewhere, but there's lots of things you can read online about this approach as well, so you can look up some other tools to try to understand it, because this algorithm has been fully, discussed online for in academia for, I guess, 20 years now, and there's all kinds of ways of describing it, but there's a starting point for you to know what it is and how we're going to use it. And then that's where we'll end, and